So today we'll just have a review of the inverse problems in geophysics. And tomorrow and subsequent days, we'll look at receiver functions and surface wave analysis and seismic tomography. So we know from theoretical seismology that the seismogram that you record at a seismic station contain information about the earthquake source and also some information about the medium through which the seismic wave generated propagate. So then given the seismogram at a source, can you see my pointer?
Yes.
Okay, so given the seismogram, which is the displacement, then we can use some mathematical techniques to retrieve information about the source, which is the moment tensor, or the Green's function, which is the elastic parameters of the medium through which these waves propagated. So then in reality, seismology is really an inverse problem. It's an inverse problem issue where we start with the end product, which is the seismogram, and try to gain some information about the source or the earth structure. And the inverse problem here is mostly fairly complicated if you compare to the forward case of where we try to predict the seismogram given a seismic source and the physics of wave propagation in a medium. So here we look at some definitions about inverse problems, and we see that we look at the forward theory. So what is a forward theory? The forward theory is a mathematical process of predicting data based on some physical or mathematical model with a given set of model parameters. So let's say, for example, let's say we want to predict the two-way travel time of say of a given earth structure. Let me annotate. So let's say we have a structure of the earth, okay, where each layer is having a layer thickness di, so d1, d2, and velocity v2. I'm just using the mouse, so this is going to be a horrible, but okay, d1 and d2. Then if we want to predict the two-way travel time, which is the wave that goes down and back up, then we know that the model that we need to use is, we know that velocity is what? Distance over time. And now we want time. We want to predict time. So time is distance over velocity. And so this two here is because the wave is going up, down and up. And so this will be our model, okay, that we use to predict the data. And the thickness, these layer thicknesses and the velocities is what we call the model parameters. So then schematically, you have a model parameters, you're given a model parameters. So let's say if we're given a layer thickness, say, 10 kilometers, 15 kilometers, and we're given the velocities of each layer, say 3.5 kilometer per second and say 4.2, then we can predict the data. Okay, so this is the forward case. And then the model will be given by this relationship, and the thickness and the velocities are the model parameters. But defining these model parameters is very flexible. So for example, say we drill this structure here, and we can determine from this drilling the layer thickness. Okay, so let's say this, we know before that the layer thicknesses are say 10 and 15. In this case, these are fixed for each layer. So there are no more model parameters. They are given for the problem. And the only model parameters that we are actually interested is then the velocities, okay? So then the inverse problem is then given these given these travel times, which is the data. I have to also clear my things a bit. So clear drawings, okay, all of that. So Given the data, then the inverse problem is to use some model, okay, to estimate or predict the model parameters that were used to predict the data, that were used to obtain the data actually. So for an inverse problem, it is very important that we can solve the forward problem, because else we don't know the relationship between the model parameters and the data. So this is all that inverse theory is about. We start with the data and we go back to find the model parameters that generated the data. Some other definitions are the model. So the model is the mathematical relationship between the model parameters. And can you see everything, or it's just me that this thing is blocking?
Yeah, we can see.
Okay, I can move this here. So model parameters, and such as the layer thickness that we just saw, and the data. And the model parameters will then be the numerical quantities or unknowns that we are attempting to estimate. So in this case, layer velocity, or say layer thickness, if we don't know them, or both of them. But the interesting thing here is that it's very flexible defining the model parameters. We see that in the previous model, we are defining the velocity is in the denominator, okay? Now, if we use the slowness, which is the reciprocal of the velocity, then we can define the travel time model as xi di, okay? So the summation. So now, instead of a nonlinear relationship where we have the velocity occurring in the denominator, we have a linear relationship. The data is a linear relationship with the slowness, layer slowness. Okay, so now we have changed our model parameters from a nonlinear case to a linear case. So it's very flexible how you do it. But then there is a penalty to pay for this, in that when you change your parameterization, your solution also changes. Okay, you have to be careful with this. The solution changes with the parameterization, and then there are ways to analyze how the solution changes and if the solutions are acceptable or not. And so, and then the data are the observations that you make, and some examples of inverse problems. So in medical tomography, when you go for your x-rays, it's an inverse problem, because they inject the x-rays, they know, and then they get the data, and then they try to retrieve some medical parameters and everything. And I guess you did this, yes, last week, earthquake location, where you have your data and you try to determine the epicenter of the earthquake, and moment tensor inversion, S structure retrieval, and body waves inversion, which we will do maybe tomorrow, and so on and so forth. And so the goal of inverse problem or inverse analysis is then to estimate a set of some model parameters. Okay, so the velocity, the thickness, whatever that you want. And also, another important thing is to set the range of the acceptable model parameters, the bounds. What that means is that, let's say we are looking for layer velocities. Okay, then if the velocity is a random variable, what are the bounds? What are the limits? Is it from 1.5 to say 4.0 for say a crustal structure, or is it from 0 to 15? You know, this is not realistic. So then it helps us to set some bounds for our model parameters that are acceptable. And we can also use the inverse analysis to estimate formal uncertainties in the model parameters. So how uncertain is our estimate of the model parameters from the true model parameters that were in nature, and also how sensitive the solution is to noise in the data. You know, I mean, our data usually always contain noises. So then what it means is that we can determine from our solutions if, say, the data changes by, say, 2%, there is a 2% change in the data, will our solution change significantly, or the solutions that we'll get will be close to the previous one that where the data, say the original data, okay? And also you can use that to inverse analysis to see if a more complicated uh, or say more model parameters uh, are significantly better than a simple model. So what this means is that, say, for our travel time problem, we define a two-layer problem, okay? So in nature, we don't know how many layers or how many parameterizations are there. So this is fairly a simple layer. Say, we'll say this is a layer 1, layer 2, and let's take this as a half space. So if we are to retrieve a velocity model, in this case, we'll be looking for a velocity V1 here, V2 here, and V of the half space, okay? What it means by a complicated model or a more model parameters is that if we how do I change the color of this? Okay, yeah. If we should add additional layers, so that now we are looking for V1, V2, V3, V4, okay? That's the solution that we get with this, say, 4 layers over half space, significantly improve the solution compared to just using the 2 layers, okay? So then we see these dynamics because you should know that when we say use a 4-layer model, then the computational cost is increased. So we want the model to be as simple as possible that best fits the data, okay? So then we do these investigations and see how our solution changes when we use a more complicated model or a simple model. So now we look at some nomenclatures. So let's say associated with inverse problems. So let's say we make some n measurements, okay, of data. So these measurements, our observations, goes into what we call the data vector D here. And we are interested in estimating some M model parameters. Then these model parameters we'll put them into some other vector M, which we call the model parameter vector, okay? So, okay, and then the relationship, which is the model that relays the data, and the model parameters can be explicit or implicit, or linear or non-linear, okay? So this is an example of an explicit linear relay model where this M1, M2 are our model parameters, and D is the data. So we can see that there is a linear relationship. So the models that multiply each other, or there is no second degree of each model. And in this case, this is a nonlinear relationship. And we say that this definition is explicit because we can separate the data on one side and the model parameters on the other side. Okay, and that's what it means by explicit. And then the implicit is where we cannot separate the model parameters and the data, so they occur together on one side of the equality sign. And if we define our model like this, then we can simply write them in matrix notation as D, which all the data vectors go into this vector D, and our model parameters go into vector M, and then G will be the coefficient matrix. Okay, this is basic linear algebra. So then our problem that we're interested in solving is given by this, D equals to GM. So, so the D is an n dimensional data vector. M is an m dimensional model parameter. So the number of model parameters, the number of data is n, and the number of model parameters is m. And then the G is an n by n matrix. So we know from matrix multiplication why this is m by n by m. And then, so this on this slide is showing us some simple example of how to construct these matrices. So let's say we have data, D1, D2, some model parameters, so two data observations, model parameters M1, M2, M3. So M is equal to 3. Then we can put this into a matrix notation by putting all the model parameters in M and the data in D, and then this will be the coefficient matrix. So this we have 2. The first equation goes into the first row, 2, 0, minus 4. These are the coefficients. And then we can see that this coefficient matrix G, it's the linear combination of these model parameters. So M1 will multiply this, the column 1 of G, M2 multiplies the column 2 of G, and M3 multiplies column 3 of G. So these are the linear combinations. Then we can get this. So we set up our system of equations in matrix notations as this. So these are given. Okay. So these are some examples of forward problems. So say we have, we make some N temperature measurements, Ti, at different depths, Zi's. Then the data goes into the D vector where all the N temperatures are, are in a column vector D. And if we assume that the temperature is a linear function of given by Z, a linear function of Z, so then there is a linear relationship between temperature and the depth. Then the model parameters in this case will be A and B. So where A will be the intercept and B will be the slope. So for a linear model, our model parameters here will be A and the intercept and the slope, whilst Z will be some auxiliary information. So then what it means is that given any Z, if we know these model parameters, the intercept and the slope, then we can calculate the temperature. And in matrix notation, this is how it comes in, okay? So you can see that the two model parameters are here, and this is the data, the coefficient matrix. But if we assume that temperature is related to the depth by a quadratic equation, then now in this case, our model parameters will be A, the constant term, the linear term, and C, which is the quadratic coefficient. Okay, so this will be our model parameters. Now our model parameters will be 3. And so given any Z, so now this coefficient matrix is constant. So let's say if we are given any Z, we can compute this, and then the unknowns are the A, B, and C's. So this is how we cast our forward problem. And another example is acoustic tomography. So here we are given a block, a rectangular block made up of small square blocks of equal sizes. And so and these blocks have, they have the same size but different velocities. So if we put a source here and we want to measure the travel time that a wave or some sound effect travel through this block, so we have a receiver here, then the small blocks that affects this the travel time that we get for this experiment is just 9, the block 9 10, 11, 12. Okay, so this the combination of these how do you call it? These blocks give the travel time data, whilst these ones doesn't affect the information the travel time data in this case. So and then the forward problem will be, say, if we want to compute T1, so T1 will be this one. Then now here we are casting the velocities as slowness, so it will be the slowness of the first block, the second block, and third and fourth block. Okay, and then to define the complete matrices, we'll have a lot of zeros. So this is a sparse matrix, where we see that in the case of T1, the linear combinations are the x1, so x1 multiplies the first coefficient element here, x2, that, and that. So this is how you define it. So in this case, we have the model parameters are 16, okay? And each data is given by some linear combinations of these 16 model parameters, some of which are 0, as we can see here. So this is how we defined also this forward problem. So then our main problem is that we are given some data and some model parameters that we need to estimate, and we would like to find the model parameters in the fair world where everything is nice and smooth. This G matrix will have an inverse. Okay, we'll have a mathematical inverse, so that M is just, okay, it's here. M is the estimate of the model parameters will be just the inverse of G times the data vector. But usually G doesn't have an inverse. You know, we cannot get really a mathematical inverse for G. So we kind of have to use some mathematical techniques to find the best available G that we can use to make this estimate of the model parameters. And this is where all this inverse problem is, you know. I mean, for in geoscience, because our G matrix is definitely singular, so there is no inverse. And definitely not square to start with. So usually, like this one, if we consider this matrix, it's definitely not square, so you're not going to get an inverse. Okay, so then the inverse problem is to find some appropriate inverse of G that we can use to estimate the model parameters, and then we can compute how well these estimates are from the true model parameters in some case. Okay, so then inverse problems based on length. So say we make some observations, the observed, and then we use our forward problem to predict some data. So we know the G, we know some model parameters, and then we can make some predictions. Then, because in the case where we have a mathematical inverse for G, then G D predicted should be equal to D observed, so that the difference, which we call the residual, the difference between the observed data and the predicted data, will be equal to 0. Okay, but this is not the case. It's hardly that we have a mathematical inverse. So the predicted data, it's definitely not equal to the observed data. And so we try to find the next best thing is to make this residual vector, which is E, we define as E here, to be close to 0 as possible. So we want this vector to be as small as possible. And this is what we mean by the objective function. So in reality, our objective is to predict the data precisely, but we cannot do that, okay, because our matrix, our system is not square, it's singular. So we look for the next best thing, which is to minimize the residual vector and use to minimize the residual vector, which is the difference between the observed and the predicted data. So our objective function is cast as finding the length. So, the magnitude of the residual vector is the length. So we find the length, we try to minimize to find the minimum length for the residual vector, which E is given by D observed that. And so this is the predicted. So this is how you cast an inverse problem. And this is what we try to solve now. And we're going to look up procedures to solve this problem. Okay, so it's a minimization problem. So then we define the data error vector, which is also what we just said is the residual vector as the difference between the observed and the predicted data. And the model parameter vector is M as always. Okay, so then the inverse problem is, since it's a minimization of length, we look at some definition of the length of vectors, which is called a norm. So here we define an L1 norm. So basically L1 norm is just if we have a vector E, if E is equal to the elements E1, E2, say E3, then the L1 norm is just the summation of these, the absolute values of these elements of E. And the L2 norm, which is what we usually know, is then E squared plus E, okay, how do you call it? E squared, 2 squared plus, okay, and the square root of this. So then the LM norm is just any integer value where M is any integer value there, 1 over M, and then you just find the power of M, the elements of M, and then this will be the LM norm for any M. And this L infinity norm is just to find the maximum value of these elements. So let's say if the second element is has the maximum absolute value, then the L infinity norm is equal to L2. Okay, this is how some ways to define length. And depending on the problem you want to solve, you use different length norm definitions, and then of course your solutions will be different depending on which length norm definition you use. And next we look at what we call the total misfit. So we call this a total misfit. So we know that this is a misfit. So we use these names interchangeably, misfit, residual, or data error vector. So this is the misfit, or residual, total residual. No, okay, so total misfit is not a vector. It's how do you call it? It's a scalar quantity. So this is the inner product of the residual vector, and this gives the total misfit. So in reality, this is just E is just say L2 square, because we don't put the square root over. If we put the square root here, then it's just the length. So then E is just L2 squared, okay, which we define as the magnitude. So then the point is we want to minimize this E. We want this E to be as small as possible. So how do we go about this to minimize E? We first look at the least square problem. So we're given a system of equations where we have seen how to cast this in matrix notations. And then we can get what we call for the least squares, we can get what we call the normal equations, which is we just pre-multiply this G by G transpose. And then the right side also we pre-multiply by G transpose, okay? So now if we have these normal equations, this is a much more, depending on the number of independent columns in G, this is a good system. So here, this G, we can take this G transpose G will be a square matrix. It's usually a square symmetric, mostly positive definite. These are some linear algebra terms, matrix, which when the columns of G are independent, will have an inverse. Okay, so this matrix will have an inverse. So we can find the inverse of this G transpose G. And then our estimate of the model parameters will be L, which is L linear squares estimate. So in this case, what it means is that we are looking for some M, okay? But our G doesn't allow us to find this M exactly. So the least square problem is say, okay, pre-multiply this G by the G transpose such that this matrix is square, is symmetric, is positive definite. And then this, if we find this inverse and multiply by G transpose and the data, then this M is the best estimate we can get for M. So this is an estimate of this M that we want, but we cannot really estimate this M exactly, but this is the next best estimate of M that we can get. Okay, this is what the least square is saying. So this is an estimate of these model parameters that we want. So this is the least square problem. And so this is how you do this. This is just the same thing as I explained. So you're given a system, you pre-multiply, you find the inverse. So, you know, this G transpose G will have an inverse. So if you multiply it by its inverse, this will be the identity. All this will be the identity. So you are left with this SM, and then you get the estimate of M. Okay, so this is the least square problem, and here we are just assuming that G transpose G exists. Okay, so it's still possible that it doesn't exist, which one of them is that the inverse doesn't exist for sure if the columns are not independent. You know, the columns of G are not independent. So if they are dependent columns, then for sure it doesn't exist. Okay, and so this is some determinancies of the least square problem. So yeah, we have the least square solutions, and we want to determine if G transpose G exists or not. This gives depending on the columns and how the coefficients in G are posed, we can determine it categorizes the least square problem into three categories or three classes, which we call an even. So we say the problem is even determined if the number of model parameters is equal to the number of observations. So we have equal number of data and equal number of model parameters to investigate. So for example, the data is 2, the model parameters are 2. So this is an even determined problem. And if this, so this is what it means is that now this is a square matrix, okay? And then if this inverse exists, then we can estimate these model parameters exactly, such that the prediction error, which is also the residual vector, again a different name, it's 0. Okay, so we can solve this system exactly if we have an even determined problem. In the case where there is more observations than model parameters, which is what we call, so this is a square matrix. And here we see that we have a tall, we call this a tall matrix, where the matrix is tall. Then in this case, we cannot fit all the data exactly, okay? So we will find some estimate of the model parameters. This is where least squares comes in. Okay, so we find some estimate of the model parameters. This is it. So if is it the same problem? Yes, I think it's the same problem. So here, the actual model parameters, the true model parameters are 1 and 3, and these are the best estimates that we can make: 1.3, 4.8. Okay, so the data cannot no longer fit exactly. And then the third case is where we have we call the third case an underdetermined problems, where we have more model parameters than the number of observations. So usually we call, this is a simple case where it's just one observations and two model parameters, or here we have two observations and three model parameters. And we call this the fat matrix, you know. So this is, this G is a bit, how do you call it? Fatter, and the long and the least square case is taller. So here is some notes here. I'll give you this to read. So the main point is, in this case, this matrix is the rows, they are dependent rows, okay, in the matrix G, such that the G transpose G, this inverse, the inverse of this matrix doesn't exist. So if we have a system like this, then we need a different way of estimating the model parameters, because the least square method breaks down in such cases. So in this case, the next thing we look at is how to estimate such model parameters when we have this problem, and which is, we call this the minimum length solution. Okay, so here we know that the G transpose G inverse does not exist, and some prediction error is exactly 0, which normally is not true. So if you get some residual vector that is giving 0 length, then you know that there is a problem with your solution, because there is no way you can exactly predict the data. So in this case, what do? We now find the estimate of the model parameters by, I think I didn't write this, I didn't show this up, but by minimizing. So what we're trying to minimize is that we're trying to minimize the length of the model parameter vector. Okay, so we're looking for a minimum length solution. This length is the model parameter length. Okay, so M transpose M is the length. This is how you define the length. So we're trying to minimize this. So this is our objective function. This is what we try to minimize. And we can do this by, if we have, so M equals to D, is to post-multiply this G by G transpose. So we post-multiply G by G transpose, and we do that for the data. And this also is a square symmetric positive definite matrix, which will have an inverse. Okay, so we'll have an inverse operator for this, and then we can find the inverse, the estimate of the model parameters, in this case as this relationship. So the G transpose, you post multiply again by the inverse of G transpose, and then the data vector. So then this will be the estimate of the model parameters using the minimum length solutions. Okay, and yeah, but usually, oh, I didn't class, sorry. So usually this is the estimate, but it's very common to have some prior estimate of the model of the solution. So we usually have some prior estimate, so we know roughly how the solution is, or like around which point the solution is. So we'll use that as a prior estimate. And so if we have this information, we can include that in our estimation of the model parameters by putting that here. So this is our prior estimate of the model parameters. And then we this term is coming from this just this part. And then D, okay, this is the D, and G times the prior estimate of the model parameter. So then this term will be our predicted data based on the prior estimate, prior model. Okay, so just simply, if you imagine that the prior estimate, in this case, we use a prior estimate of the solution to be 0. So M in this as brackets is it's 0, then this goes away and this goes away, and then what is left is just this one, which is the estimate of the minimum length solution. But if we have some prior non-zero prior estimate of the solution, then the estimate of the model parameters is given by this relationship. Okay, and this is just the expansion of this relationship. So now we have gotten two ways of estimating model parameters. So we have the least square method, which when we have independent columns, okay, so a tall matrix, we get the estimate of the model parameters in this way, in the least square. And when we have a fat matrix, where in this case they are dependent columns, but the catch point is that in this case they are independent rows. Okay, so the rows are independent. So then we use the minimum length solution, to estimate the model parameters. So these are the two ways of estimating model parameters. And then we look at some weighted measure of length. So this is what I just talked about is just the, how do you call it? The simple case, the simple case where we think that our data doesn't contain any errors, okay? But when we look at the actual case where our data contains some errors, then we have to weight the data, how much, how important each data is by some weighting metrics, okay? So because this data, say we have some data that is we know that it's wrong, then the weight we want, how do you call it? The weight that we want for this data should be very small. So in the actual computation, we don't want it to affect too much the estimation of the model parameters. So we kind of repose our problem as a weighted measure of misfit. So we know that we are looking for a misfit vector, okay, E. But in this case, we want to use a weighted measure of the misfit. So the misfit is given by the residual, the length of the residual vector, and we define E as E, small e, so the residual transpose WE and E. So this is a matrix which we call the weighting matrix. So that E will be a weighting matrix. So now we want to minimize this problem, not this problem. This is the case where we think that all the data are, the data variances are all equal, okay? So, or there is no error in the data or something. So now if our objective function is to minimize this, this problem, and how do we define the W? So W is an M by N weighting matrix. And we usually take W as the covariance of the data, inverse of the covariance of the data matrix. So this is the covariance matrix. So what we mean by a covariance matrix is we define the covariance matrix, I think. So, okay, in simple terms, we know that when we have some data, say we're given some velocity data. So this is a random variable, okay? So V1, V2, V3. Then we can find the variance of the data, which is sigma square, okay? And then the standard deviation will be sigma, okay? So if we have two observations, say V1, V2, or two random variables, say V and, well, let me use X and Y, so it's simple. So these are two observations. Then the variance of X of X will be X squared, okay? And the variance of Y, data Y, will be Y squared. And then the covariance is the relationship between how X and Y varies, okay? And that will be what we call the covariance, is X and Y. So it's the variance of X and Y. And we can put this information in a matrix. So we will get X squared here, Y squared on the diagonals, and then the variances here. Okay, so these are the covariance and these are the variance of the random variable. So this is how you define how do you call it, a covariance matrix of the data. Now, in this case, if we assume that the covariance, so this term, the sigma xy term is 0, okay, so that all the off diagonal elements are 0, then we say that the data is uncorrelated. So there's no correlation between X and Y data values. And so then the covariance matrix will be given by this diagonal matrix, which are just the variances of the X and Y data, okay? And so the inverse will be, if you define the inverse, will be just the reciprocal of the variances, okay? So the variances. And this is given by that. So the variance it's squared, so then just the reciprocal of the variance squared. Okay, this is just the variance, sorry, or the standard deviation squared. Okay, so this is how you define the W. So this is what goes into the W. Okay, these are the variances that you use. So you can imagine that if we in the unweighted case where we are trying to minimize E equals to E transpose E, then, well, in this case, there is a weighting, there is a weighting matrix here, but which is just the identity matrix, okay? And then we get this. But if we think that the data, there is some variances in the data, then we actually uses that these variances goes onto the diagonals of the covariance matrix, and then we find the inverse. So this is what we mean by weighting and the weighting matrix. And if we define our weighting matrix WE as the inverse of the covariance, then our least square solution now will be begin by this relationship, which is the same, but now we have this weighting matrix here, you know, that give more weight to some data and less weight to some. I don't think I have the relationship here, to some other data. So this is just some weighting metrics that we put in here. Okay, so it's almost the same solution, but with some weighting metrics in there. So we put it here and we also weigh the data here. So that's the weighted least. So we call this solution the weighted least square solutions. Okay, and we can do the same thing for the minimum length solution. So instead of minimizing M transpose M, we choose to minimize M transpose some times some model, some weighting matrix WM and times M, where in this case WM we are taking the covariance of the model parameters. Okay, so it's defined as the same in the same sense. And if we replace M by some M minus some estimate, some period estimate of the model parameters, then our objective function will be, so we are replacing this M by this will be M minus brackets, angle brackets, average, or whatever you want to call it, transpose. Okay, so this M goes there, then your weighting matrix, and then M minus some square, the prior estimate of the model parameter. So now this becomes our objective function. And if we do the same analysis, if we go through the analysis, then the weighted minimum length solution is given by this. So where we have the inverse of the weighting matrix, and it's all here. Okay, so this is how you deal with noises in the data. when you want to weight the data by some weighting metrics. Here, this slide shows some other choices of M where we can use as the, so in the previous case, we used the inverse of the model covariance matrix, but we can use some matrix D transpose D, where D is the first derivative matrix. We call this the first derivative matrix or flatness matrix, or in some books you find it's called the smoothness matrix. What it means is that once we have our once we have our estimate of the model parameters, so we have M1, M2. What we mean by smoothness is that we don't want M2 to be too far from M1. So our the changes in our model parameters are very close close to each other. So the changes are not very too much. So this is what we use as we call a smoothness matrix. Or we can use a roughness matrix, which is the second derivative matrix, as the model covariance, the weighting for the minimum length solution. So so now we have looked at the actual least square or minimum length solutions, and we have looked at weighted minimum length solutions. But then there is also more to it. Usually both the unweighted and weighted problems are very unstable. Okay, so what it means is, or for mathematicians, is what you call ill post, or it's near singular. So in this case, your solutions might not be really correct. So how we go about this problem in this case is to use some what we call some damping parameters. So we try to damp the solution such that we deviate from fitting the data actually, so our system becomes a bit more stable. Okay, so it's just a trade-off between the getting the best fit and getting a stable solution, some stable matrices. So we then do some weighted, so you can have some weight, you can compute the weighted least square solutions, or the weighted damp least square solutions, or just the damp least square solutions without weighting. Okay, so in this case, if uh, here I'm just is showing that this is the weighted least squares, this is the weighted minimum length solution, and then we can form some new objective function as E sigma or epsilon squared, where epsilon now is the what we call the damping parameter, and L is what was given here. This is the minimum length in the minimum length case, and E is the total misfit that we saw in the least square case. Then the objective is to minimize this system, okay, with some damping parameters. And then if we go through the analysis, then we can find the estimate of the model parameters, what we call the weighted damp estimate, will be given by this relationship or that relationship. Okay, and it's really this is just the difference when you have in this case you are looking at the least square operator, and in the other case it's just the minimum length operator. So because we have combined the two objective function, we are kind of solving a multi-objective problem. Okay, so we have one objective function and another objective function, and this is some weighting, how well we want to how do you call it, constrain these two objectives. So if we want to really focus on E or E plus, so we are just combining the two objectives and trying to find the best solution in this case, and this is given by these relationships. So this is it. Okay, So now we're done with mostly the linear case, where we have looked at ways of, so all that we went through is just to find some estimate of the G inverse, okay? So using the least square method or the minimum length method to find the G inverse. So in this, so here, let's say for example, all this comes with the G inverse. This comes about just because we don't have the G inverse, okay? All this is the G inverse. So once we have this, we can find some estimate. We can find the estimate of our model parameters. Now let's look at the general case where the relationship between the model parameters and the data is nonlinear. Okay, so how do you deal with this? I mean, most problems is in this form. It's not a simple linear relationship. So in this case, when we have how do you call it? When we have a nonlinear relationship between the model parameters and the data, what we do in practice is to linearize the problem. So we cast the nonlinear problem as a linear problem, and how we do it is by this procedure. I mean, there is a whole explanation on the steps to go through, but in summary, you start with some starting model. So you have, say, you're given this problem, you start with some starting model, M naught, and then you use this starting model to predict the data. So then the predicted is say G, okay, M naught, okay. So we predict this data, and then we can find the misfit vector here, delta C, which is the observed data minus the predicted data, so the residual vector. Okay, then we form our G matrix. How we form our G matrix is by taking the partial derivative of this function gi with respect to all the model parameters. If you go through the analysis of deriving the least square problems, I think we'll look at this maybe tomorrow or in the afternoon lecture. We just you find the partial derivative with each. So if they are, say, two model parameters, then it will be so G, I think GM1 and GM2. Okay, so you find the partial derivatives with respect to these model parameters, and then you evaluate these derivative at M naught at the start with the starting model. Okay, so you evaluate this. So then you get a G matrix. So what you can see that just we're going to make some iteration. So then the G matrix this time is not constant. It changes with each iteration. Okay. Then in this case, we have find a way to estimate the G matrix. Then our linear problem, then we can cast this now as a linear problem where we try to so in the previous case, in the main linear case, we have D equals to GM. But now we are looking at the difference, the misfit vector equals to the G, which is now our coefficient matrix, and the difference in the model parameters. Okay, how do we find this? Is then now to estimate delta M, we use delta M will be equals to G inverse delta C. Okay, let me clear this so we can understand again. So let me just repeat here. I think I'm not clear here. We find the misfit vector by the difference between the observed data and the predicted data. And now we compute our G matrix by finding the partial derivative of this function, okay, and evaluating these partial derivatives at the given model parameters. Okay, then we try to solve this system. This now is a linear system. So this C is coming from here, and this G is coming from here. And then now the point is to find delta M, where delta M is equal to G inverse delta C. But then you ask, oh, there is no G inverse. Okay, yes, there is no G inverse, but this is what we have gone through for the past, I don't know, 20 minutes trying to find a way of estimating G inverse. Okay, so we know some procedure to find some approximate inverse of G. So this G inverse, once we have this G, we can use the least square method or the minimum length method to find this G inverse. And then we use that inverse to multiply the misfit vector to estimate the model parameter, the changes in the model parameters. So once we have these changes, okay, these changes, we can then form a new estimate of the model M1 by adding these changes to our starting model. Okay, so now this becomes our improved estimate of our model parameters. And then we use this to recalculate the predicted data. Okay, so now this hat will be G. We know G from here, G M1, okay? Then again, we find delta C, and then delta C now will be different, and then we find the changes in the model parameters again, and then we improve this. So then this goes to M2, M1 plus delta M. So we iterate this until the changes in the model parameters are very small, or when your number of iterations, you exceed your maximum number of iterations. So this is how you recast a nonlinear problem linearly, like you use a linear method to solve the nonlinear problem. This is it. We'll go through these steps we'll try to write some code for earthquake location using these steps, so we'll have a better feel of how this works. Okay, now the next part of inverse problem, we cannot talk about matrices without saying anything about eigenvalues and eigenvectors. I don't think the mathematicians will be happy. So we just refresh on eigenvalues, and this will be, how much time we have? I don't know, 20 more minutes. So okay, well, it's just left with a small part, and then we're done with the first section. So let's use that to talk about eigenvalues. So say you're given a system A x equals to B, then if this A is square and non-singular, then we know that we can find the eigenvalues of A, okay? And what that means is that this square matrix A, if we multiply some vector x, okay, then the transformation AX is such that x doesn't change, but it's just some scalar quantity. So what it means is that if we have a matrix A and we multiply by x, this x it outputs almost the same x, but multiplied by some scalar parameter. And this scalar parameter is what we call the eigenvalue, okay? And this S will be the eigenvector. So how do you call it? Geometrically, this is, say we have some vector X, okay? And then we have some matrix A. Usually, if you do AX, A times X, which is a matrix times vector multiplication, you get a different vector, say V, okay, that is in this direction, a complete different vector V, okay. But if X is the eigenvalue, is the eigenvector of A, okay, this is the eigenvector of A, then the X that comes out from this multiplication is just the same X, this same X, where either the length of X, sorry, it should be on the same straight line, has been increased, or we get a shorter X or a reversed S, okay? So the X is the same, but then there is some change in the direction or the length, there is a change in the magnitude. The scalar quantity that either reverses the direction of X or extends it or shrinks it is lambda, which is the eigenvalue of A, okay, of X. So this will be the eigenvalue associated with the eigenvector S for this the square matrix A. So this is how you get the eigenvalues and eigenvectors. So how do you get an eigenvalue and eigenvector for some metrics? We have this system, so we have this problem, and what we do is to bring lambda x to the left side, and so x will be the same. We take s out, and lambda is just a scalar quantity, so we multiply it by the the identity matrix, so we can subtract, we can do a matrix subtraction. And then the solution is just the zero vector. And if we find, so to find the eigenvalues, we set the determinant of this matrix, which is A minus the lambda times the identity matrix. We find this determinant, and this matrix is usually singular, so the determinant is zero. That means it's singular. And then we solve this system. Solving this system, we get what we call the characteristic equation, which is a polynomial of order m. And so this polynomial of order m by the fundamental theory of algebra will have m roots. So we get different eigenvalues, m eigenvalues actually, some of which might be repeated, of course. And then once we have all these m eigenvalues, we can compute the eigenvectors using these equations. And the catch point here is that why we're interested in finding eigenvalues and eigenvectors, mostly in most physical problems, is to do what we call decompose the metrics, okay? So what we mean by decomposition is that we have a matrix A. We want to decompose it, as in we want to find some metrics, different metrics, such that we can write A as, say, X lambda X inverse, okay? So also another name for decomposition is diagonalizing. So this A will be, say, some metrics that have some elements on the off diagonals and on the diagonals, okay? And we want a much more simpler matrix, which will help in easy computation, such that this A goes, the information in this A can be written as some diagonal on the diagonal of some matrix, okay? This is the goal of getting eigenvalues and eigenfunctions. We want to decompose A or diagonalize A into some diagonal matrix. So how do we do this is that we solve that AS equals to lambda X. Okay, let me clear this up so there is space. So we have A X lambda X. Okay, so we have m eigenvalues. So say xi equals 1 to m. Okay, then it means that we'll have x eigenvectors. It's difficult, sorry. So x eigenvectors, okay? So each eigenvalue has an associated eigenvector, okay? Then we can write this A, okay? A is still the full matrix, as a matrix x1 up to xm, okay, equals to a matrix xm, x1 to xm, times another diagonal matrix. I'll explain what this means. I1, lambda 1. I don't know, I'm now slanting it. Sorry. Okay. Okay. Can you see? Or I should rewrite it. Hello? Can you see?
Yes, yes, yes.
Okay. Yeah, because it's so m1 to lambda 1 to lambda m. So then what goes into this matrix X here are the 1 to m eigenvectors, okay, of A. So we put all the, so we know that all the eigenvectors are, say, some column vectors, okay. So this is x1, x2, up to xm. We put all these column vectors into the columns of some matrix X, okay. So all these eigenvectors forms the column vectors of the matrix X, and we put the same thing here. But then the eigenvalues goes on the diagonal of some, let's call this a capital lambda matrix, okay? So that we can see that it's just a linear combination. So everything here is 0. The off-diagonal elements are 0. So that lambda 1 multiplies x1, okay? And x1 here will be just the linear combinations of, A will be a linear combinations of these columns of x. So then we can just, it's just the system, it's just the same system as this. S2 lambda 2 x2. Okay. So we just decompose, we just put everything in these matrices. And then in this case, we can say that we want to, when we want to diagonalize A, we just want this, all the eigenvalues on the diagonal of some matrix lambda, okay, a capital lambda. Let me clear and then let's explain. Okay, so so the columns of AX, X lambda, these are the so this will be the eigenvector matrix X, eigenvector matrix X. This is the eigen value matrix on the diagonal on this lambda, okay? And then A, so if we have independent, I have to, this is important, independent eigenvectors. What we mean by independent eigenvectors is that there is no repeated, okay, so there can be repeated values. But then each repeated eigenvalue can have independent eigenvectors. That's possible. That's the degenerate cases. If this is the case, such that each eigenvector has a different eigenvalue, then A can be decomposed into this product of these three matrices, where this will be these are just the X matrix are just the, how do you call it, the eigenvectors, and the eigenvalues goes into this, okay? Then why we do this, that is then that it's easier to do some computations on the matrix A. So let's say if you have A square Okay, so let's say if A is say 1, 2, 3, 4, then A squared will be this times this, no? Okay, these two metrics. So we have to do some computations of some metrics computations here. This is heavy, but if we are able to decompose A as, if we are able to decompose A as X lambda X inverse, then A squared will just be X lambda squared X. Okay, so it's just to square the eigenvalues on the diagonal matrix. This is easy. It just, you can compute this for a large system, and it takes literally seconds to finish the computation. So this is why we want to do this. And also, I will see in the afternoon section, it helps us in getting what we call another form of inverse, which is singular value decomposition for any metrics G. Okay, so this is the diagonalization of A, or decomposition of A into some diagonal matrix lambda. And okay, these are some other informations. I picked these notes from, I think, some book by Strand. So let's see what's important here. Okay, so this is the same thing as I explained. So these are now these diagonal metrics. If we want to just find the diagonal matrix, is just to find, this is the inverse eigenvector matrix, and the A, this is the actual data matrix, and this is the eigenvector matrix. Okay, and then this gives us the diagonal A. So A now is diagonal in this case. Okay, it's simple. And the other, oh, okay, I need questions. The other thing is that, oh, what did I want to say? Yeah, so what is nice is that now we have these eigenvectors, okay? We can we can make them, how do you call it? Octagonal. We can make these eigenvectors octagonal, so we can use Graham-Schmidt or something to make the eigenvectors octagonal, so that when they come into the matrix, when they come into the column of X, say, XM, now this matrix S will be an octagonal matrix, say Q, if we use Graham-Schmidt on these vectors, so that we have Q1, Q2. And orthogonal matrices are the best to have, because then if we want to compute this inverse here, we don't have to go through the whole analysis of Gaussian and elimination to compute these inverses, but it's just for an orthogonal matrix or octonormal matrix, it's just the transpose is equal to the inverse. Okay, so this is also why we go through all this analysis. So you can, once you have the eigenvectors, you can use Graham-Schmidt and make them octonormal octonormal vectors, and then you put these into the matrices X. Now X will be an octonormal matrix, so it will be Q, and then A. So this relationship now, this one could be written as Q transpose A Q equals to some diagonal matrix. So this is the decomposition of A into some diagonal matrix lambda. Okay, yeah. So that's it for the first part. Questions? Hello?
Hi.
Yeah,
Yes.
it's okay, it's okay.
Was it too fast or?
It was okay, it was okay. Can you hear me?
Yeah, I can hear.
Okay, yeah.
Oh, okay, cool.
Okay, but I have a question.
Yeah, please.
On equation is 3.70.
What?
Equation is 3.70.
Well, I
don't know
really,
if
I really took this thing from 3.70. I really, if you could say where under which section it is, then 3.70.
just in,
This one,
yeah, yeah, yeah,
3.70. Yeah.
yeah. Is there any relationship of this fusion with the Taylor expansion?
With what?
Taylor expansion.
Taylor expansion. No. Uh, this is not a Taylor expansion. Because no, this is pure matrix manipulation. Okay, so Taylor expansion really doesn't come in here. This is weighted, yeah. So this equation actually, the derivation of this equation, if you go through the mathematics, it actually uses Lagrange multipliers instead because it's the minimum length solution, whilst the least square derivation uses the partial derivatives. So the minimum, you said you find the partial derivatives and then you set them to 0. So this is partial, it's coming from a partial derivative of the model parameters. This is coming from the Lagrange multipliers. It's not Taylor expansion. Taylor expansion comes in when you try to linearize the nonlinear problem. So in actual fact, you find this G and then you expand this by this around this M naught. Okay, so this is where you use Taylor expansion if you look at the mathematics. But for the minimum length solutions, you don't need Taylor expansion. Yeah, if you look at the derivation of the linearization of nonlinear problems, here you use Taylor expansion. And then you discharge the higher powers, but not in the minimum length solution.
Okay.
It's just say here, it's just that if we forget about this, okay, and forget about this negative, this term here, forget about it is that let this, this is a prior estimate. Let's set this to 0, okay? Then in this case, a minimum length solution is just the actual thing that we found before, okay? It's just this, D. But we're saying that, maybe because we are looking for minimum lengths, maybe our model parameters we have some information about our model parameters. This is what we call the prior information, okay? And we want to include that. Let's say we know that our model, it should be around something like 1.0. This, sorry, 1.1. Say 2 models. This might not be the exact thing, but we know that it should be very close to this this solution. Okay, then this vector is what is going to go through, is going to go into this term here. So it's just some prior information, just some belief. Okay, I mean, if you want to talk in terms of probabilities, it's just some belief in which area, in which space, sample space, our solution is. Okay. Yeah. So it's not really Taylor expansions. Yeah.
All right. Yeah. So again, why is this weighted matrix related to covariance of D?
The weighted it's related to the covariance of what? D.
Yeah, of D, the inverse matrix of covariance.
Yeah, because so each data, if I should write this, if I remember this equation correctly, it should be something like this. I think say I squared, yes. So I squared. Okay. So the the variance of each data gives, say you have some data, how do I explain this? Say, the variance is the spread. How, say, if they, how far some value of the
From
data
the mean,
is from the mean, okay? So if we want to we know the mean and we know that the variance and the variance of the data, then we want the data to be closer to the mean as possible, okay?
Yeah.
So if there is an outlier, it causes the variance to be bigger, right?
Right.
And this outlier is probably an error in the measurement, okay? So if this data with a big variance, we weight it as the same as the one that is closer to the mean, then it's going to affect our solution, okay? Because it's wrong, okay? So let's say if say 3 has a variance of, I don't know, 50 something, that is big, and all the other data have variances of 1. If we take this data 3 as the same weight as all the data, then it's going to shift our solution towards some, maybe our solution should have been 2. Because of this this error in this data, our solution will probably be 23. Okay, so it shifts our solution completely. But if we should use a small weight such that, no, I don't think this definition will help you. So if we should use a small weight such that we weight each data by the variance, so it's divided by this variance, okay? If we divide, so it's a summation. Here is a summation. So you see what I wrote here? It's a summation. And each data, if each data value is divided by its variance. So if all the data has a variance of 1, then it will be the data value divided by 1, which is the data itself, okay? But this data 3 that has a high variance, which is 50, which is likely wrong. So in the summation, it will be D3 divided by 50, whilst all the other data points will be divided by 1. Now this will be a very small number.
Yeah.
Okay, so then its contribution to the total misfit will be very small. Okay.
Yes.
Yeah, so this is why we use the actual the covariance matrix. Else, if we just pick only the D3, then the contribution will be very high. Okay, so then our solution will deviate from the true estimate. Yeah, so this is why we use the data covariance matrix.
Okay, thank you.
Because of this reciprocal thing here, because the variance is in the denominator. Okay, so the inverse actually. Okay, is that clear? Hello?
Hi.
Is it clear?
Yes.
Okay. Okay, so if there are no more questions, we end the one section here. In the second part, we'll be looking at singular value decomposition, which is the best next thing from, say, using statistical methods for inverse problems. But we're not going to look at probability problems, statistical problems here, like Bayesian inversions and everything. But yeah, this is the next best thing, or the equivalent best thing to generate an inverse. And most geoscience problems is the inverse. Yes, we still use the minimum length inverses, but or the least square inverses, but this is the highlight of inverse theory actually. So in the afternoon section, we'll look at this, and then we'll probably look at some examples, and we'll call it a day. Okay, So enjoy your lunch. See you later.
Thank you.
Thank you.
Bye.
Ciao, bye.
Bye.
Thank you.
Yeah, Simone,
Smalley,
how are you?
Fine, fine.
how is the preparation for the exam?
You will pass today, yeah?
It's finished because yeah, I have the exam this afternoon.
Oh, okay.
You have your exam this afternoon
Yeah. So tell the professor that I won't be able
to
to
join. Okay,
join.
okay,
So
okay,
don't wait
okay.
for me.
Okay.
I'll check the video after the exam.
Oh, okay, cool.
Yeah, the video are there, Simone.
And Professor Bobby sent us some summary about the results. So
Yeah.
Okay, good. So good luck.
Okay,
Best
thank you.
wishes. Yeah, bye-bye.
Jacobo,
Yeah, Innocent.
how are we going to access these videos, these recorded videos?
You said?
How are we going to access
The videos, recorded
Yeah.
videos.
Yeah.
Do you have access to the other videos?
Yeah,
Yeah.
I sent you
Oh.
Innocent.
Yeah, I use this the other. Okay, the other link you sent.
Yeah, you can find everything there.
If you have
You
access
go just
then
yeah, you can go to the ESP section, second term, okay, second term ESP section, and you have to choose both if it's in YouTube, the OCM are in YouTube or in internal repository. Okay.
Okay.
I think that this course is in YouTube section in the link that I have sent you. Okay.
I will check everything. I think I'll find it.
Yeah, you can find all the courses there.
Okay. Thank you, guys.
Okay.
Okay. Ciao.
Bye.